So just to reiterate one more time, if you go back into your Unit 2 script for the MANOVA, you need to change the URL, add XX onto MV data. MV data XX dot RDS or RDA. And then the one that we're using today is the MV data. And sorry about that mix up. Before we start on the actual thing, I'm going to go over kind of a brief crash course over the drill that we did for the Logistic Regression unit of the grad stats course last year, because this will show several different things that I think do a great job of highlighting what it is that we're doing here, why we're doing it, and it's a more simplified example. There's only one independent variable that's used. So the generalized linear model, one of which is logistic regression using that logic link, allows us to free ourselves from some of the assumptions of the general linear model. So for instance, one of the assumptions of the general linear model is independence, right? Well, you don't have to worry about that when you're using generalized linear models, because you can model that dependence via mixed effects models. You don't have to worry about normality of the residuals, because if it follows a Poisson distribution, you can use that instead of a normal distribution. So you can get around some of the assumptions of linear models by using the generalized linear models. So the example that I'm going to give today is from this data set that's in the CAR package called Mirage, and all it is it's U.S. women's labor force participation. The only variables we're going to be worrying about today is LFP is the labor force participation, just dichotomous yes or no, or is this woman in the labor force, and then K5, which is the number of children under 5 years old. So if we wanted to see, like, all right, does the number of kids under 5 that a woman has, affect her labor force participation? First, if I just fit it as a regular linear model, so just, labor force participation regressed on the number of kids, under the age of 5, run our load the right data set. We run our regression, right? And then we say, like, oh, yeah, this is crazy significant. Look at this. And then, because everything in zero, so, the labor force participation for women with 0 kids is 0.61, and for each additional kid, it goes down by 0.2. Just how you would interpret a normal regression output. But the problem with this is once we look at our assumptions, so if we look at the normality assumptions in this, quite clearly our residuals don't follow that normal distribution. You can see, like, and these should fall more or less along those lines. So normality isn't looking too great. If we look at the constant variance, again here, like, when you look across all of our different diagnostic plots, it becomes very clear that, oh, wait a second, when you have this dichotomous outcome, we violate all of these assumptions, which is why we use the generalized linear model. We use that logistic regression. So here's what the actual data look like, that these women are in the labor force and these are not. And then just grouped by how many kids under 5 they have. And so before, when you're looking at the linear models, you can look at trying to transform things and blah, 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 but point is, there is no transformation that will work that makes this a linear thing and satisfies the assumptions. We have to use those that generalized linear model. Now, as far as all I'm doing here is I'm creating a thing, probability from 0.01 to 0.99, and then the odds are the probability divided by 1 over the probability. And so when we look at this, we have our probability down here and our odds. We see that our probability is bounded by 0 and 1, right? Odds is bounded by 0 and positive infinity. Then when you switch to the log odds space, which is what you use in the logistic regression, then it goes from negative infinity to positive infinity and has that kind of S curve to it. All right. So if I just take those, take the log of those odds to make the log odds, and now you see here's what our log odds looks like. So instead of modeling it with a linear model, when we're using logistic regression, we're going to use GLM instead of LM, generalized linear model. And the only other argument that you add is family equals binomial, and that's how you're telling it that we're using the logistic regression. Or at least it defaults. There are other binomial links to use besides the logit. If you talk to any political scientists, they love probit instead of logits. And I don't know if you can speak to the difference, but I've tried to figure out like what's really and truly the difference between these. And anywhere you read, basically what they say is 6 of one, half dozen of the other. Probit and logit will almost give you the exact same answer every time. And nobody can really explain why you would use probit instead of logit, so I just stick with logit because that's what I know. But anyway, so now we're going to fit this logistic model instead, mod G. And now when we look at our things, instead, now we're talking about log odds of things. So the log odds of a woman with no kids being in the labor force is 0.48, and having kids under 5 decreases those log odds by 0.87. That's easy to interpret, right? Like thinking about log odds is just super, super intuitive.
If you're anybody but me, because they don't make any fucking sense to me.
So in order to make that more interpretable and make sense, you can change those log odds to odds or probability, depending on what your purpose is. In order to change your from log odds to logs, you just need to exponentiate your output. And so this exp function, so I'm going to exponentiate these two coefficients, and then we can see that. So now this 1.61 and 0.041 is the odds of a woman with no kids being in the workforce is 1.61 to 1. And then it changes by a factor of 0.41 when they have kids under 5. As far as, and we'll get into more nuanced interpretations and stuff when we get to the actual unit. Like I said, I'm just trying to kind of run through this for a general overview. This script, if y'all want to look through it, because I explained a lot of stuff in here, it's available on my OSF thing under my course materials. But one more thing that I wanted to point out is then to switch to probabilities. There are a few different functions that you can use for predicting things, and this is one of the things that we'll be doing today. So we have, there's a function called predict, and if you include this type equals response, then the output of that is going to give you the probability. So you tell it, like, I want to predict, like, based on some model that I've created and using some data that I've created, like, give me the prediction of the probability for this new data. So in this example here, conceptually what it's doing is I say, like, okay, let's say this woman has 3 kids under 5. So if I just create a data frame with that one variable, because I only have one predictor in this model, And so if I set that to 3, like, what's the probability that that woman is in the labor workforce? This is also what you'll use when it comes to plotting, because one thing as far as visualizing logistic regression is that if you're in that odds space or log odds space, you cannot plot the raw data with the model itself. The only space that the raw data exists is in its raw form, and the only thing that you can plot over that raw data is that probability. So you can use the predict functions to generate, some line and bands for probability and plot that over the raw data, but probability is the only thing that you can plot alongside the raw data. And with that said, we'll go ahead and get into today's stuff. So I added a unit 3 filter to the data set. We'll go ahead and filter out people who aren't there. And I also added this dep2.in and dep2.f.
So I'm getting an error saying that unit 3 filter not found when I run that line.
Did you add XX to the?
I did.
Yeah, no, don't. XX is unit 2's data. So I also created dep2n and dep2f, and I wanted to briefly go over like how we made that and why we made it the way we did. So if we look at the histogram and summary of our continuous dep2, the depression at time 2 variable, and we want to dichotomize that into high and low. So when we look at our summary statistics, we can see that like the third quartile is 2, and we can also see on the histogram, like we see this pretty clean break. So given that 2 is the cutoff for the top 25% versus that bottom, seems like a pretty good cutoff. So that's where our dep2n and dep2f comes from. Anyone that's higher than 2 for their depression in time 2 gets labeled as high with a 1. Anyone that's less than 2 gets labeled as low and 0.
I'm going to just take a quick pause because we're moving into the homework assignment, and I want to give a little bit of a broad overview of what we are doing for our logistic regression. Okay. So let's grab our assignment. Does everyone have their homework assignment up and ready? Okay. So the thing that we're going to be doing today is we're going to be figuring out if we can predict kids who are going to be elevated in clinical depression at time 2, meaning in high school, from some variables during middle school. Okay. So that's our basic question here is, can we categorize from this longitudinal perspective from some middle school data which kids are at risk of developing clinically elevated depression at time 2. And we are counting clinically elevated as above 2, although the measure itself may not correspond with that, but let's just go with it for now. Okay. So we're going to do a few different things in this particular lab, and I don't appear to have my homework assignment with me. Do you have it?
Yeah, I got it right there.
Okay. I have output, tons and tons of output, but I actually don't have the assignment. Okay, so the very first thing that we're going to look at is just a straight up, all the predictors going into the model at the same time. Can I use this set of variables to predict depression in high school among these middle school kids? And the variables that we're using are?
Sex, birth region, depression at time 1, self-esteem at time 1, and discrimination at time 1.
And friends.
And friends, yes.
Okay, so we're basically looking at a set of psychosocial variables at time 1 and looking at whether those predict depression at time 2. So of course, depression at time 1 passes prologue, right? We definitely want to include that in our model. But we're also looking at whether US versus foreign-born kids are more at risk for developing depression in high school, whether male or female children are more at risk of developing depression, whether kids who endorse low self-esteem at time 1 versus higher self-esteem are more at risk for developing depression, kids who experience discrimination right, during middle school. And then also kids who have had some social isolation, meaning that they don't have a large group, network of social support or friends. So those seem like really reasonable variables. It makes sense that we would want to use them maybe to identify kids at risk. This sounds an awful lot like some of the work that people do in some of their labs. So that's what we're doing today. We are going to then extend this later on, and we're going to be looking at some potential moderation in predicting clinically elevated depression. So we'll be creating some interaction terms that allow us to see whether, for example, and I'm making this one up because I don't remember exactly what it was, but like whether discrimination experiences in the face of low self-esteem particularly elevate risk, right? So as an example. And then the final thing we're also going to be doing is looking at some hierarchical models, so looking at basically what is the incremental utility of certain predictors added on to other predictors. Like, for example, we know depression predicts depression. That's not really going to make psych, science. But can you say, okay, can my set of predictors above and beyond sort of depression help me predict something unique? So we're going to be doing a few different logistic regression equations over the course of this assignment, but all of them are concerned with trying to categorize or identify kids who are likely to be clinically elevated in depression during high school from these middle school variables. Okay?
So we have one DV.
Right, so what Austin was describing for you is, of course, depression at time 2 is actually a continuous variable. And so if these were my real data, like my hard-earned dissertation data, I probably would not dichotomize it because continuous variables have more power, and I'd probably do a regular regression. But that's not good for teaching. For teaching, we need something with a dichotomous outcome. And so it felt like a good thing to take a look at our depression variable, dichotomize it, and then use that in order for us to learn how to run a logistic regression. The other time you might take a continuous variable and chop it up like this is if your variable is very non-normal. Okay. So you guys mentioned when we plotted these that this didn't look particularly normal, and you're not wrong, right? That's what my adolescent says. I'm never right, but I'm just not wrong. So you're not wrong. But the skewness and kurtosis values were actually pretty within range, meaning we could have treated it as a normally distributed continuous variable. But again, for our purposes, and for many other purposes, you might actually be interested in like diseased, yes or no, dead or alive, clinically elevated depression or not. So there might be reasons why you would dichotomize. So that's kind of the general overview of what we're doing, and then we're going to walk through bit by bit. And Austin just described for us how we decided to dichotomize the depression 2 variable, given that it's not obvious what we would do. So if it's not obvious, plot it, take a look at your quartiles, take a look at the distributions, and in our case, we're going to try to predict that upper 25% in depression, which happens to coincide extremely nicely with a natural break in the data. Okay.
All right, so then the last couple things before we actually get into the homework questions and the model. One is that since we're using sex and birth region, later we'll be using the numeric versions, which I have coded in the data as -half and +half. But for logistic regression, we need to make those 0s and 1s instead. So here, that's all I'm doing is I'm adding half to make it 0s and 1s for both of those. And then for the factorized versions of these two things, we need to set the contrasts. Normally the contrasts do just default to 0 and 1, but if you run it before you set the contrast, you'll see that it says like -0.7 and 0.7. That's a vestige of this data was originally an SPSS data file, and as things carried over, because I never changed the contrast, it had put in some polynomial contrast coding for whatever reason. So all we're doing here is we're setting the contrast for sex and birth region to 0 and 1, so that now if we check what our contrasts are, it'll tell us that United States is coded as 0, Central South America is coded as 1, and then for sex, males are coded as 0 and females are coded as 1. So what's the nature of the variables that we would use for logistic regression?
Dichotomous DV.
Dichotomous DV and
continuous predictor.
continuous or categorical, at least one predictor. The real key is a dichotomous DB. If you have more than two categories, there's multinomial logistic regression, but that's a different story. And so yeah, in general, the dichotomous DV and one or more continuous or discrete predictors. What are the assumptions that we make with logistic regression? So we know normality of the residuals is not one of them.
That there is a bimodal distribution. Would that be one?
It's not one of the assumptions. Take a look at your lecture slides. There are very few assumptions that we make here.
Yeah.
The DV or linearity of the logit?
Linearity of the logit.
What the hell does that mean, by the way?
Assumption that continuous predictors have a linear relation with their natural log.
Wow, that was so perfectly stated. What does that mean?
So y'all remember earlier when we were talking about that, like transforming by using that logit function and how it transforms things, but basically after you use that logit, is it now a linear relationship? Like it's not in its raw form, but does that variable interact with its natural log in such a way that it is now linear?
I see confused looks.
We'll explain more when we get to actually checking the linearity of the logit. Let's not get ahead of
Is
ourselves.
that basically just saying that after you transform it, like you take the log of it, that basically it's still related to what it was originally?
Sort of. So all linear regression equations assume kind of that linear relation among the variables that are part of that equation. And if you remember from our lecture slides, in this case we have that linear relation, but it actually ends up being the power to which we raise something, which is why in its raw form it's not linear. So we still need that piece to be linear, but in order to check that, we have to take the natural log of continuous variables. We have to multiply them. I think I'm having aphasia here. We have to multiply them by their natural logs, like the natural log by the continuous variable, and that, in the end, should tell us whether we have linearity in that linear equation that is then raised to, that is the power. If you look at your lecture slides, we raised u to that regression equation. Right?
Think of it this way, like step away from like a variable and its natural log, and we'll just say a and b. If you have a and b and you take the product of them and put that in a model, and that's significant, then that tells you that there's an interaction there, which means at one end of this, things are different than at the other end. If it's not significant, then that tells you like, hey, this is like just kind of all along one thing. Now put the continuous variable, and b is the natural log of that continuous variable. When you multiply these together, do you get something that's significant because it doesn't follow that linear thing. When you multiply a continuous variable by its natural log and get that interaction of the two, like now does it follow a linear pattern?
And the weird thing about it is we don't usually ever put in the variable and its natural log into a prediction equation. This is only something we do to check the assumption that the continuous variable is appropriate for logistic regression. So like depression 1 is a continuous variable. We are not going to put depression 1 and its natural log into our logistic regression. But in order to make sure that we're meeting the assumption of linearity of the logit, we have to first check it against its natural log. And we will do that a little bit.
So
What other assumption? Oh, go ahead.
What if you have a dichotomous predictor?
Only straight line relation between dichotomous predictors and other things, so you can never violate linearity that way. So which is why sometimes when people do have violations of linearity of the logit, like I don't think we're going to see them today. I think all our variables are fine. But if we were to have a significant interaction term between a continuous variable and its natural log, then you can try to transform the original variable, or you can chop up the first one. You can categorize the first one into a set of dummy codes. Like if depression 1 ended up being problematic for us, we could decide that we would have our predictor be elevated depression at time 1, yes, no, instead of the continuous. So if you violate linearity of the logit, you can deal with it by categorizing your variable or trying to transform it. You can't leave it as is. You do want to check that.
So besides linearity of the logit, what's our next assumption?
Like multicollinearity?
No multicollinearity or singularity, or outliers, for that matter. And then 2 more that we're looking for.
And that's multicollinearity of the predictor variables.
Yes.
Your outcome variable is discrete or categorical.
Right. So we have the categorical DV, dichotomous.
No outliers.
Mm-hmm. Correct.
Independence of
That's what it
errors.
says here.
Independence of errors. And then the final has to do with the size of your cells. Basically, you have to have enough data to be able to make the things. The ratio of the number of cases that you have, the number of observations that you have, and the number of variables that you're using has to be sufficient. If you only have 10 participants and you're trying to use 7 different predictor variables, it ain't gonna happen. All right, yeah, so once again, our assumptions: linearity of the logit, no multicollinearity or singularity, no outliers, independence of errors, categorical DV with 1 or more IVs, and then the cases to variables ratio needs to be sufficient.
Could you say the last assumption one more time?
The ratio of the number of observations you have and the number of predictors that you're using has to be sufficient. You can't use too many predictors if you don't have enough participants.
Are you familiar with chi-square tests? So in chi-square tests, you technically shouldn't be interpreting your chi-square if any cell is less than 5. So if you're looking at, I don't know, male, female, depressed, not depressed, if you have any cell that's like 0, you're not supposed to interpret your chi-square. Logistic regression is just chi-square expanded. So, but the same rule applies. You can't have cells that have no people in them and then actually be able to interpret the LR.
For these assumptions, are most of them for continuous predictor variables?
Multicollinearity and linearity of the logit, definitely. The outliers is outliers among the solution, not among the independent variables. Meaning, I don't want to be super wrong if I predicted there's like 100% chance of rain, and in actuality it was like 0%. That's a fucking outlier, right? Like I was really, really, really wrong. If most of my predictions were accurate, but then I have this one that was really, really off. So we don't want outliers in the solution. Meaning people for whom we just did a terrible job at predicting their probability.
All right, so now we'll go ahead and fit our model, name it just mod, M-O-D. And so to do this, like I said, it's very similar to just a regular linear model, only now we're going to use GLM instead of just LM. And we'll tell it our data equals DF. And we want to predict dep2n regressed on sex.f plus birthregion.f plus dep1 plus SE1 plus discrim1 plus log friends1 And then after you get that last predictor variable in, just put a comma, and then you'll tell it family equals binomial. And so again, that's telling this generalized linear model what distribution we're wanting to use for this, which is that binomial distribution. If you're using Poisson or whatever, like you would put in some other family, some other distributions here. And so now we'll fit that into a thing called mod. And then, so that brings us to number 3, where now we start checking these assumptions. So first thing is multicollinearity. To check for multicollinearity, we look at our VIF, our variance inflation factor, and our tolerance, which tolerance is mathematically 1 over VIF. So to get our VIF, there's a function in the car package called VIF, and you don't have to enter the car. I'm trying to get better about at least using the explicit on the first time we use something to help point to where functions are coming from. So this VIF thing, and you just put in your model. Like I said, for tolerance, it's just 1 over VIF. So we can run both of those things. And now when we look at our output, what we're looking for is a tolerance that's greater than 0.1 and a VIF that is less than 10. So here where we run VIF, we have it for sex F, the VIF is 1.04, 1.01, 1.25, blah, blah, blah. Like clearly, all of our VIFs are well below 10. That all looks fine. And then our tolerances, which we're looking for greater than 0.1, we're up in like the 0.7s, 8s, and 9s. Like clearly across all of these, they're good. So our tolerance and VIF are both fine, which tells us that like as far as multicollinearity goes, like we're in good standing. We're good to go here. Any questions about that? Because this next part is this linearity to logit thing is going to
We have an
take
error
a
message here. I'm telling you, it does that weird thing sometimes. When you look
So it's saying there's no linearity between them.
Yeah, so while they problem solve that, so you can check multicollinearity in a couple of ways.
Oh, sure.
What's one of the ways you can check it? Yeah, just running your bivariate correlations, that's one of the ways. The other way, and you might have seen this already when you took the class in regression, is by looking at the set of predictors and then these things called variance inflation factor and tolerance. It's functionally very similar. This is a little bit more technical, but it's basically saying, is there redundancy among the predictors to an extent that it will create some problems in the stability of my estimates in my regression. And so when you have tolerance values that are very small, about 0.1, we want everything to be close to 1. And when you have variance inflation factors that are very large, above 10, what that's basically telling you is that there's a high degree of redundancy among your set of predictors. And so that's problematic. You need to look at like which variable is highly redundant with the other ones based on its VIF, and maybe think about either excluding it or combining it with another one into a single score or doing something like that. You could absolutely have just looked at our correlations. This is just sort of another way of doing it.
Any other questions before we move on to linearity of logit? All right, so I've gone ahead and started this part for the linearity of the logit, where again, what we need to do is we need to check basically we add into the model, we're going to include the product of each of our continuous IVs and its natural log. So, I mean, there's any number of ways that you could do this. As far as like if you wanted to, you could just like take each of the continuous variables, multiply it by its natural log, and store that as some new variable and add those created variables. But as we've discussed plenty before, especially when it's something like this that you literally only need to check this to make sure this is good, but you'll never actually need to report these numbers or anything. You don't need to save these variables. You only use it for this, and then we never think about it again. So I will create the interactions within the model itself. Now, when you're working with these formulaic expressions, with the tilde, plus, and asterisk and whatnot, R interprets this as, including also the main effect of this other thing, and then the main effect of this thing. And that asterisk, it doesn't mean multiplication, it means the main effect of each of these things plus their interaction, right? It doesn't see this as a mathematical expression. These are more akin to logical operators when it's in the formula like this. If we were over here on this side, on the dv side, you could do math in there. So I could say dep2n plus 0.5. Let's just say that our dep2, instead of being coded as 0 and 1, was coded as -half and +half. We could just say dep2n plus 0.5, and it would make 0 and 1 the actual thing. But on this side of that tilde, it doesn't work that way. It interprets that as, that interaction or main effect covariate type symbol. So what we have to do is we have to use a thing that inhibits the interpretation as this, and instead tells R, hey, I'm talking about a mathematical operation here. And that inhibit function is just using wrapping it in a capital I. So if I do an I with parentheses, and now whatever you put inside of that I, R interprets as a mathematical computation, not as this stuff. So now that we have that I, we'll create our first interaction of dep1 times the log of dep1. And then our next continuous variable is SE. So we need the I, and we'll tell it SE1 times the log of SE1. We have discrim. And then the last one is the friends. However, to remind you, we already, this log friends1 variable that we have is already the natural log of that friends variable. So what we actually have to do is go back and use the original non-log version times we already computed the log here. So in this case, we'll have also, as a reminder, that original friends log, you can't, or the original friends1 variable had zeros. You can't take the log of something with zeros, so we're going to pull that original friends variable, but also add that 1 to it, just like we did before we took the log in the first place. So we'll say the friends1 dot ORIG is what I had named the original untampered with friends variable plus 1. And all that in parentheses as its own one thing, and then multiply that by just log friends1. And at the end of this, we'll add our comma, because that's all of our continuous variables interacting with their natural logs. We need to tell it our family equals binomial. And then I'm just going to pipe that straight into summary. And now once we run this, for this particular thing, the only thing we're interested in are these interactions down here. And as you can see, none of these interactions are significant, which is a good thing. That's what we want. We don't want significant interactions of anything interacting with its own natural log, because that's when we start getting into weird space.
Austin, can you repeat that about the significance?
We don't want it to be significant. In this case, significance is bad, because if there is something that's significant, then that's telling you, like, once you convert this over to its natural log, things go weird. Like, it doesn't fall in where it should be. We do not want significance on this linearity of the logit.
So, okay, so we don't need the sex or the birth region because it's categorical?
Right.
Gotcha.
Yeah, so let me, if you don't mind, I'm gonna take a second,
I
because,
figured this would be a minute on this page.
yeah, thank you. You're starting to get me. Austin now looks at me like, he's like, go ahead, jump in, I know you wanna say something. Okay. So to test linearity of the logit, this is what we had to do. We basically took all of our continuous variables only, because those are the only ones for whom this is important. And we created a new regression equation, dep2, which was predicted by dep1 plus dep1 times its natural log plus SE1 plus SE1 times its natural log plus, what did we have, discrim1 plus discrim1 times its natural log plus friends1 plus friends1 times its natural log. Okay, so a couple of things we want to say here, because they went really fast. First of all, these are actually the only ones we care about when we're trying to look at whether we violated the assumption of linearity of the logit. We're not looking at the results from these variables at all, okay? All we care about is whether the continuous variable times its log is significantly different. Basically, if there's a significant moderation of factor, it's significantly different from linear, okay? And what we're hoping for here is no significant interaction between continuous variables and their natural logs. If we have that, we're violating linearity of the logit, okay? So that's the first thing. Is that clear to everybody? Okay, so that's why we made that long equation that we made. And the i's in there were an R thing, because if you had just written in dep2 plus, or dep1 plus SE1 plus discrim1 plus friends1 plus dep2 times log, it would have said, or dep1 times log of dep1, it would have interpreted as, let me take the main effect of the log, the main effect of dep1, and their interaction. And we didn't want that. We wanted it to mathematically just multiply those two things so that we have this. Okay. That's why we had the inhibit function. Okay, the other thing, are you going to prove that for us?
Yeah, I was going to try anyway.
The other thing that happened, and it all happened very fast, so that's why it's good for us to take a step back, is that we had to do something funky with friends, right? So friends didn't follow the pattern. So the reason friends didn't follow the pattern is because friends was already log transformed, okay? So if we needed to look at the original variable times its log, well, we already had the log, so we really needed to go back and put the original variable in. The problem with the original variable is that the original variable included kids who said they had no friends, 0 friends. And when we made a log, we had to, you can't log transform something where there are 0 values. And so when we had originally, back in the very first day of drill, had decided to transform friends1, which had so much skew, we basically took friends1, we added 1 to it, and then we took the log. And so if we're going to create this term to check linearity of the logit, we have to use the original, but we have to add 1 to it, just like we did when we transformed it. So that's why there was that sudden little like, oh, right, friends1 plus 1 times the log of friends. Okay.
Making sense?
Can you repeat the part, where you were saying like, it was a beautiful sentence and I cannot remember it, so I won't say
Thank God we have it recorded. What was it about?
Just how, when you want it to be not significant because something linearity.
Yes, these terms, the way we check for linearity of the logit is by multiplying our continuous variables times their natural logs. And so we don't care about the actual continuous variables here, we only care about their interaction terms. And if we find that these interactions between, say, depression 1 and its natural log, and by interaction I just mean the multiplication of the product, right? If we find that any of these product terms for our continuous variables is significant, that suggests significant moderation, which is a violation of linearity of the logit. I don't know if I said it as beautifully as the first time, but that's the basic idea. So we're doing all this, like with a lot of assumption checking. We have to do a lot of shit, but then we really only care about one piece of it. So this is the only piece that we actually care about. These interaction terms, these products. And we want them to be non-significant.
So I'm getting slightly different p-values.
Are you comparing it to this?
Yeah.
That's because this is wrong. This is when I took off the I, just to show, like, once I took off the I off dep 1, it gives us just the log of dep 1 as one thing plus the interaction and log down here. And so that's why we wrap it in that I, because we don't want the log of dep 1 to be a,
We don't want a main effect of log.
predictor. We just want those mathematical interactions of the two. If I run it again now, you should get the same thing.
Just a R-related question. So if we were not interested in kind of telling R, like, all right, on this side of the regression equation, I want to do a mathematical formula, we could do the interaction term with the colon?
No, you would, you would like create the variables on the front end and then just put in those products
Okay.
as the whatever. So you could call it, dep 1 int and arrow dep 1 times the log of dep 1, and then the next one se1 int, and then instead of having these i's and stuff, you would just have plus dep 1 int plus se1 int, etc.
So the reason for that is because in this equation, we are actually never looking at the main effects of the log versions of the variables. If you just default to the right side to use dep 1 colon natural log of dep 1, then you're going to get dep 1 main effect, natural log main effect,
Gotcha.
and the interaction. But we need to get rid of the main effect of the log. We only need the continuous variables and their products with their natural logs, not the main effects of the natural logs.
That makes sense.
So the two ways to do it are create the interaction terms and store them as variables in your data frame, and then you just write your dep 1 plus the next, the interaction term, SE1 plus whatever. Or in this case, we did it all within the model by inhibiting the way that the right side of the model is interpreted by R, and instead saying, okay, don't do this thing where you think I'm asking you for all the main effects and interactions. Instead, do the math that's in between these parentheses.
And this would be for any non-transformed variables compared to their log.
Any
Continuous.
continuous variables.
Continuous. Non-transformed?
Well, we did it with friends too. We had to go back to the original friends and then multiply it by its log transform.
Like this implicitly already is log friends 1 original
I
plus
get
1.
that.
But if we'd had a square root, for example, let's say that we had square root of self-esteem, then the equation would have been dep 2 predicted by square root of self-esteem 1 plus square root of self-esteem 1 times its natural log, not going back to the original self-esteem. These are great questions.
Anything else before moving on? All right, so we've now checked our assumptions, everything's looking good, and it's time to start moving into some interpretation stuff. So the first question asks, what is the percent correct classification on the baseline model? So that's asking on the baseline model, like this logistic regression makes predictions about whether somebody is a 0 with low depression at time 2 or a 1, they have high depression at time 2. What percentage of the time is the baseline model correct? Well, what is the baseline model? The baseline model just makes the same prediction for everyone. And the prediction that it makes is based on which is the most occurring thing. I mean, it makes sense. If given literally no other information about anything, what prediction are you going to make about an outcome? You're going to rely on the base rate. Whatever has the highest base rate is going to be, like, statistically speaking, the most probable outcome. So you predict that outcome for everything and then see how off is our prediction. Because it's all zeros and ones, one way that you can think about this is looking at the mean of the outcome, and if it's below 0.5, then you know that it predicted 0 more often than it predicted 1. If it's higher than 0.5, you know that it predicted 1 more often than it predicted 0. So if we look at a table of our dep2.f, to see, like, this is just what we coded. Low is the more commonly occurring outcome. As far as, and so basically what this is asking now, all right, so if low occurs more often, the baseline model just predicts low for everybody. What percentage of the time is that correct? So it's correct 1,780 times out of all the occurrences. If you wanted to do everything from within the data and not have to then say, 439 plus 1,780 to get your total, and then do 1,780 divided by the total and such, you could call just that first. So our 1,780 divided by the length of the variable and we'll multiply that by 100. And again, the reason I really appreciate just it becoming habitual to not explicitly enter stuff into scripts, but rather extract from the data, is because, what if we go back and realize, like, oh, wait, we've got a handful of 17-year-olds that we didn't get parental consent from. We have to remove these 5 people from our data. And now, if you just type in, 1,780 divided by the total, when you go back and rerun your script, like, now your baseline classification is wrong. So this is why here, it doesn't matter. You can literally do whatever you want to the data, and it's going to give me the actual accurate, baseline classification. But here we see 80.2% is the percent of correct classification of the baseline model. 80.2% of the predictions are correct because it predicted low for everybody, which means it was right for 1,780 of the 2,219 predictions that it made.
I have another question. In the data frame, dep2.f is coded as 0 and 1, correct? Because that's something that we did. So is another way to do this just to ask for the mean of dep2.f?
Yep. Going back to well, you'd have to use the dep2.n, but yes. But that at least tells us which one is more.
Why do those numbers not agree? Or no, they do agree? Because it's 0. Right. Right. So that's the base rate of the least frequently occurring.
Yeah. But at least taking that mean will let you know which one was used in the baseline model. Because again, if it's below 0.5, 0 was the prediction more often. If it's greater than 0.5, 1 was the prediction more often. Is that making sense? When you look at the mean of the numeric version of it, If the mean is below 0.5, that means that it predicted 0 more often than it predicted 1. You have more zeros than ones. If they're perfectly even, your mean will be 0.5. If you have more zeros, it'll pull that down below 0.5. If you have more ones, it'll push it up above 0.5. So when you look at the mean, you can at least know which outcome was predicted more often.
So in this case, we have an average of 19.8% of kids were scored as 1, and 80.2% of kids were scored as 0.
Is it normal to do 0 for low halves? Or low
Yeah,
halves?
logistic regression can get a little bit wonky about what counts as a 0 and what counts as a 1, and we're going to encounter that in a little bit because your 0 is what's called your reference group. So when you talk about odds, you're always talking about odds relative to something, and the relative to something is what the reference group is. So for example, what are the odds of developing depression for girls relative to boys? Right? Not just in general, what's the probability of girls having depression? That's a different question. This is like, what is the elevated risk or the relative risk for girls versus boys? For the outcome variable, most often 0 is the absence of the condition and 1 is the presence of whatever it is you're looking for. So it sort of depends on how you're labeling it.
Sometimes it might be just a question of like, what are you more interested in? Kind of like with just regular linear regression, that if you're wanting your coefficient to represent this group specifically, then that's the group you set at 0. And then 1 will be like, all right, the difference between these groups or the increase, from one group to the other instead. So sometimes it's just a question of which are you more interested in interpreting, but I mean, you can always get the other one. But when we get down to the actual part of interpreting the odds and stuff, that's you'll see that those contrasts pop back up. So that's one thing I always do is rerun my contrast so that I can see there and make sure like, okay, yes, males were coded as 0 and United States was coded as 0, so that you can remember as you're making those interpretations. It's always advisable to check your contrasts when you're interpreting these outputs, just so that you don't accidentally, flip those around.
So, and relatedly, this is now for your write-up, okay? Because for every homework assignment, you have to write it up in APA style, and including a table is a very good idea for most of your homework assignments. So in a logistic regression table, depending on how you label your predictors, you may need to include a table note to clarify the reference group. For example, if your predictor says gender, and then you provide an odds ratio, your reader doesn't know what is the odds for. Is it for boys? Is it for girls? Like, what is it? And so if you say male gender, now we know the odds ratio is for boys compared to girls. If you just say gender, you need to include a table note that says the reference group was females or males or whoever was coded as 0. If you put birth region, then you need to put a table note that indicates who was coded as 0 or the reference group. Otherwise, you could say foreign born, which is what is the odds ratio of foreign born relative to US born for developing depression. So just be very careful and considerate about how you label things and how you write them up. Your reader can get very confused with good reason if you're labeling your things generically, but then you're not clarifying somewhere what's the reference group, which got coded as 0, which got coded as 1.
Yeah, I was just gonna pull up real quick to show.
Something also to look at in your article critiques, because you'll see that published oddly on more occasions than probably should be the case.
Yeah, the same thing goes for like in the tables, whenever you have figures, same thing, include in that figure caption like what each of the variables is and indicate, if it's gender, like, F equals 0, like whatever, that way, because otherwise without knowing what is set as 0 and what is set as 1, you can't interpret anything, it makes no sense. So you do definitely always need to include in write-ups, table comments down at the bottom, the notes, or figure captions, like what's what as far as how things are coded. Anything else? All right, so now it's time to actually start looking at some summary stuff. How many iterations did it take to converge on a solution, and what does that mean for the relative stability of the solution for this? This is part of just the summary. So if we run the summary of our mod, it outputs this information. Down here at the bottom, it'll tell you the number of Fisher scoring iterations is 4. So this solution converged in 4 iterations. If you're using SPSS, it'll tell you 5. And I don't know if SPSS is doing something weird differently under the hood, or if it just counts, like if it starts indexing at 1 or something. So I don't know. Doesn't matter. SPSS will tell you 5. But literally numerically everything else except for one other exception in this whole thing, you'll get the exact same results in SPSS and R.
How much did you guys talk about converging and iterations in prior classes? Has that come up before?
A little bit.
Let's spend a minute on that too. This is more stuff that it's helpful to know. We're going to really care about it next time when we start talking about exploratory factor analysis and confirmatory factor analysis. Let's just take a very simple regression of any kind. It could be logistic, it could be, whatever, any kind. Say depth 2 is equal to some constant, right, plus B1 times depth 1 plus B2 times self-esteem 1. Let's just keep it really nice and simple for the moment. No logistics, no nothing. When you put this into the computer and you basically say, help me predict depression at time 2 from these variables, the computer is going behind the scenes and basically starting with some random values, trying to plug shit in to create these values that maximally distinguish or predict with maximal accuracy this variable. And it's a little bit like playing a guessing game, right? Where like I'm thinking of a number between 1 and 100. I can only tell you if it's higher or lower. What are you going to guess, And so you might start by guessing
50.
Higher.
75.
Lower.
60.
Higher.
65.
Yes. In 4 iterations, instead of 100, in four guesses, you guys figured out what number I was thinking of. Okay? It would be super inefficient if you had done it by, is it 1? Is it 2? That's like what a 3-year-old does. It's pretty cute, but it's very inefficient. So your computer is basically efficiently trying to come up with values for these B's, or in this case, these odds ratios that maximally predict or differentiate people based on these scores. Okay. Iterations is basically the equivalent of how many guesses did it go through. How many versions did it have to plug in and then adjust? So it starts with some random numbers, and then it says, okay, if I go up on this value or down on this value, do I do a better job? Okay, what if I tweak it this other way? And every time it looks at whether it's getting colder or warmer, or it's higher or lower. And what you really want is you want small numbers. You want it to be able to very efficiently get to a value for these B weights. And if you do that, if it has a small number, small is subjective. For the regular regressions we run, typically 25 or lower is what we would consider like a small number. Small is good because it means that the computer not only quickly found a solution, but it's likely suggests it's a very stable solution, meaning that it's not capitalizing on some wonkiness in your data, but that they're really solid estimates, okay? And so that's what we're hoping for when we ask about how many iterations, how many tries did the computer have to take. I have fitted models before where after 50 tries, the computer's like, I'm done, I can't figure it out. Every time I change a parameter, something else weird happens and I just can't figure it out. I have fitted like large SEM models where it's 2,000 iterations and it still doesn't fit. Those are problematic models. That's where you need to go back to your data. 4, great. Yeah.
Are they will it usually give me like something unreasonable, or is it arbitrary?
It's usually what it means, but it's usually because you have a very wonky variable or value in there that's really throwing everything off, and it's creating these conundrums. Like, for example, if you were saying, have you ever played a guessing game with someone who actually didn't know where something was? Like, this happened to me as a mom. My kid was playing hot or cold with me, and then I was confused because I'd like get over here and she'd say warmer. And then I'd get over here and she'd say cold. So I'd get back here and she'd say cold. And I'd get here and she's like really cold. So I'm like, wait a minute, I don't understand, because here I was warm, but now I'm cold. What are you doing to me? And then at the end she's like, I actually forgot where I hid it. I was like, okay, well, that explains it. That's a little bit like what's happening in the computer too, is like I put this value in and then you say warmer. So then I make it a little bit closer, but then you're like, whoa. And so then I go back to where it was before and you're like, whoa. And that's a little bit kind of like what happens. It's unstable, meaning it's likely not to replicate. You can't trust it. It's an untrustworthy response. So high iterations suggest low trustworthiness in terms of your B values. We don't want that. We want very trustworthy numbers. That's why we look at how long it took to converge on a solution. And the way it decides it converges is if it makes one more tweak and it didn't actually make anything better. It's like, no, I'm pretty much keeping my values. I'm good exactly where I am. This is what fits. Okay, I can't do better.
When you say wonky variables are like untrustworthy, is that like outliers? Or
It could be. Imagine if we'd used the original Friends. Remember where we had like, oh, I don't know, like 100. It is very likely that a variable like that, or it's at least somewhat likely that a variable like that would have very odd relations with other variables because it itself is so wonky in terms of its distribution. And so trying to predict what a 1 unit increase in friends or one more friend does to other variables is very unstable if you kept it in its original metric. And so if you have a logistic regression that you're running and you get to 25 iterations or 24 iterations, I would go back to the drawing board. I would not feel comfortable with that. I'd say that's a time for me to take a break, step away, take a look at my predictors again and say, what is happening here? Do I have any that don't really seem to be behaving well or not playing nicely with others? Maybe it's because it's a low base rate one. Like nobody and almost no one in my sample was not a student, and I'm trying to use student status as a predictor.
And to expand on that just a little bit, another reason that things can get real wonky real fast is if you have this one sort of kind of wonky variable and this other sort of kind of wonky variable, and then you let these two sort of kind of wonky variables interact with each other, then the wheels come off the wagon. And so, you know, oftentimes, if you're dealing with like really complex models where there's a lot of different pieces that it's having to try to predict, that's where you can deal with convergence issues from either Patrick's class or if you took Bill's MLM. You know, we talk a little bit about convergence because in the generalized linear model you have to add controls and you have to tell R like how do we want, how many iterations do we want it to have. There are different types of optimizers that we'll try to find the most elegant solution in different ways, and so sometimes you have to fiddle with some of those, but it's more or less, you know, case specific. That there's some general stuff that's like this is the go-to, and if this doesn't work and still won't converge, then start looking into like, okay, is there a different optimizer that I can use that'll work? Do I need to like simplify my model and just have a kind of a more parsimonious model?
If you have multicollinearity, you're probably going to have convergence problems. If you have some cells that are close to 0 or at 0, you're probably going to have some convergence problems. Right? So those are like, that's why it's important to check all of these.
If that ratio of cases to variables is not as good as it could be, you can run into convergence issues. Just like in mixed effects models, if the number of random effects that you're trying to predict is the same as the number of observations you have, you can run into these issues.
Did you say that models where you have convergence after very few iterations, that's also indicating strong predictors?
It actually has nothing to do with the quality of the predictors. It has everything to do with like the trustworthiness of the values you end up with. So you can end up with like, I'm really damn sure that I can't predict this variable for shit. But that's better than being like, I really don't know, I forgot where I did it, but I think it's significant, right? Like they're really not associated.
Could you scroll up a bit so I can see your code?
So is there a baseline model?
No. Well, I mean, yes, but we don't have to create one. It's already created for it. That's the null model.
Basically,
which
absent any
that's-
information.
Yeah, we only got 3 minutes, so we'll get into that next part. It's like that's the next bit of this is now looking at chi-squares to compare against that baseline model and figure out, does adding these predictors significantly improve our predictions? And that's what we'll start getting into Thursday.
Thank you.
Anything else?
For the homework that's due tonight, right? I saw in there you wanted tables of means. So
Yes,
I'm not sure.
so if you were writing up the MANOVA results, for publication, then typically publications ask you for some way to describe the findings. You could write it all in text, like the mean of the low group was this, the mean of the median group was this. That's really, really wordy. If a picture or a table can do that for you, I highly recommend you use that. And if you do have a picture or a table, then you don't reiterate that information in text. You can reiterate the pattern in text. You can say, for example, all 4 groups were significantly different from each other on the education 3 variable, the Roy Bartman step down procedure part 1, see table 1 or table 2 or whatever. So whatever you would want to actually put in a publication, that's what I want you to have. And the reason I want that is because when you leave this class with MANOVA, with logistic regression, with principal components analysis, exploratory factor analysis, path analysis, and all the other things we're going to do, you are now going to have a template for not just how to run it, but also how to write it up. So you can take it with your data and your ideas, and you can say, if I follow these things and I do all these steps we did in lab, and then I write about it the way that I'm supposed to and describe everything, I have my whole results section for a paper ready to go. And that's what I'd like. I'd like you to have that utility of having these templates for you.
When I get the MANOVA results for homework 2, should we just use the template that's in the book, the TNF?
The TNF book template is excellent. All of their templates are excellent. If you want to go outside of that, you can also look at other published works from reputable journals. But as you'll see, once you start doing article critiques, even published works don't always include all the details. Sometimes it's a space issues, but we don't know. Like you're like, maybe I could trust this person because they're a bigwig in the field, but you don't know. So follow the TNF model is probably a good way to go. Okay. All right, so you're going to be in New Orleans.
Mm-hmm.
Do you know what your schedule's like? Are you going to Zoom in with us, or should I?
Yeah, I was planning on Zooming in.